Depending on how many questions I get during your lecture, I can complete the whole slide deck or not. And we were about 10 slides short last time. So last time what we did was we went through a big bunch of things. The whole stuff in blue here we did almost all. We didn't do this. We're still missing outliers, which was what I was supposed to do last time. And the assumptions part was meant for today, so we'll see how far we'll get today, and we'll see if we can close off the multiple regression part. And as soon as we have that done, we are good to go for most of the other stuff. So first, what we missed last time, and that is finding outliers in your data. First, what they are, or perhaps better, first what they are not. The main thing to remember first is that outliers and coding errors are two very different things. So a coding error is simply a case value in your data, and you understand or know that given that you see what the value is, it cannot be correct. We know that this variable should take on 0 and 1, for instance, and there is a 4 and a half. So this is not right, it's a coding error, and usually the best you can do is simply replace it by a missing value, and that's it. However, outliers are different beasts, and there are several ways in which you can define what an outlier is. I'll go through the 4 different kinds that we typically consider, and then focus on one of the 4 to show you how the general process works. So the 4 kinds, or the 4 ways in which cases can be an outlier are actually over there. I think I have the first slide. Added this. So we're not looking at coding errors here, but at something else. First thing is the most obvious thing to look at actually is if you have cases where in a multiple regression you have a y, you have a bunch of predicted values x, and there are extreme cases in there. So if you think about the soccer data, you see that there is a player in there who is 2 meters and 7 centimeters. This is unlikely, but still possible. So in that sense, it's not a coding error in all likelihood, or if there's a player in there who is 153. Perhaps some Peruvian player or something could be indeed 153, I don't know. But it is an outlier in the sense that it is quite different from the rest of your data. The good news about this is it's easy to find. You simply look at the ends of the distribution of your variable, and then you can decide for yourself if this is a coding error or not. But in any case, you can try to figure out if there are many of these weird cases in the data, and if they are so weird that you would even argue, well, let's not look at this case because this is so different from all the rest that that one player that is 2 meters and 45. Okay, I don't think that my data is representative for that. Okay, that's an easy case. You can find these by looking at a scatter plot, or looking at a box plot, or simply looking at summaries or a tab of these different variables, and then you'll find these cases. Another way in which a case can be an outlier is if it's far from the regression line. So we're trying to fit a line through a cloud of dots with multiple regression and more predictors. It's not really a line anymore, perhaps. But that's the idea, and you can try to find cases that are typically far off from the actual value. So here, in this case, for instance, for all these, we're doing quite well, and there was one case over there that's relatively far away from the line. So we predict that one way worse than the rest, and that makes it different from all the other cases in the data. That's the second way to decide that this is an outlier, that is different from the rest. The third one is a bit more complicated. What you can try to do is for each and every case, well, first, with all the cases that I have, I run my multiple regression. My multiple regression gives me a model. I can use the model to predict my y, and I create an actual new variable in my data, y hat, with which I predict the actual y that I have. Now, one thing to do would be, okay, let's take out case number 1. I rerun my multiple regression model, and now I try to predict all cases, including number 1, from the new model that I now have run, without case number 1 in it. If I now get a value that is way different from the value that I had before, so let's say at first I predicted for y 10.5 for case number 1, now I take out case number 1, I rerun my regression model, I use that model to predict for that same first case, and now I end up with reason to look at that specific case. And what we try to do is automate that process. There are different commands in this data that will do that for you to try and find if there are cases in your data that are an outlier in that zone. And the last one, that's the one that we'll focus on in the upcoming slides, is, well, let's look at this example here. You run a multiple regression on data. Now we take out one case. We rerun the multiple regression model with the same variables in it, and now we find that the coefficients that we now get are way different from the coefficients that we had before. So at first, I'm estimating a coefficient 3.2, and it's statistically significant, and now I take one case out, I estimate the same coefficient, it's now 0 and no longer significant. Okay, this is weird. Apparently, the results totally depend on the fact that I have this one case in or out, and you don't want to have that. You want to be able to find the cases for which this is true. Yes?
Doesn't an outlier like that say something about how well you can predict? Because it can be so far away, shouldn't we incorporate that in some sense?
Yeah, let's say the general question you're addressing is, okay, suppose that I find outliers in whatever sense, then what do we do with it? And I'll talk about that in a minute. And one of the things you could argue here is, well, you know, it's measured. Up front, you started with measurement of these cases, and yeah, there could be weird cases in there, that's just how it is, and leave them in. But I'll talk about that in a minute, about what to do. Okay, so different ways to find outliers, different ways that suggest that there might be cases in there that you should give some extra attention to. And let's see how we do it. Here you see it for the other three, how to do this, but here, the one that I want to focus on is the one where I talk about the difference in the coefficients. And for that, there is a standard command in Stata that's called df beta. And in the end, we need standardized df betas, in fact. And let me show you how that goes. Well, the command itself is actually quite easy. This is the, for the other ones again, apart from the regression line, you just check where you have the largest residuals. That's not so complicated, actually. This one is about where the prediction for y is quite far off. And this is actually the one that I wanted to focus on here. To run the regression, here I have an example with 1x. Could have been way more x's as well. And the only thing that you do is then you type df beta. And what all these commands do, and this one in particular as well, is they give you extra variables in your data. And these extra variables in your data you can use to try to find where the outliers really are. And just to have that in the slide deck as well, I added here the rules of thumb that are, I think, also stated in the book. It might be slightly different even. But these are the standard rules that you need to go by. And I think the easiest way to explain how this works is simply show you an example, and then you'll see what happens. So let's go through the example. This is the soccer game. I create a variable age here, equals 2003 minus the birth year, so now we have age in years, and I'm estimating here the number of goals you score at the World Championship based on height and on age. Okay. So what we see is, well, height is almost statistically significant, but not completely. Age apparently is, so the older you are, the more you score. Okay, now I want to find outliers in this analysis. By the way, you see here also that height is negatively related to goals. It's not statistically significant, but still shows here that taller players actually score less. And you could think, well, it's easier if you're tall to score a goal, but in all likelihood, this is because the taller players in general are in the back. The defenders are the taller players. They simply do not show up at the goal of the opponent. But anyhow, we're trying to find the outliers here, and what you type is this command here, df beta. What df beta needs is that you have just run a regression before that. If there is no regression before, then df beta doesn't know what to do. But if you have it, then it does know what to do, and it generates as many extra variables in your data as you had predicted. So here we have height is 2, and here it says df beta 1, that is the df beta that belongs to height, and df beta 2, that is the df beta that belongs to age. So what happened now? Well, for instance, that df beta height variable, that is now an extra variable in your data. In case number 1, you see the difference between the estimated coefficient for height with all the cases included, and the estimated coefficient for height with that particular case excluded. Same for the second one. If we run the whole regression as we did here, and then we run the whole regression, but with the second case excluded, we check what is now the coefficient of height, we calculate the difference, and we put it in that second place in the data. So you get a long variable here with actual values for where you have cases, and apparently you do not have the cases complete for all cases in the data, but that doesn't matter so much. 2 extra variables in your data. Now you have to check for all these variables and the values that they take, which of these values are serious enough to suggest that this might be an outlier. This is actually what we needed this for. Okay, this is the rule. Take the absolute value of df beta, and you check if it's larger than 2 over the square root of n, where n is your number of cases that you have in the data. Okay, so let's see. I have 2 extra variables in my data now. Let's have a look at what they are. Well, this is the mean of that variable, so it's relatively close to 0, which is a good thing. So on average, apparently, we're not missing the mark by so much. We also see that it ranges between minus 0.18 and plus 0.24, and the df beta 2 ranges from minus 0.14 to 0.39. Okay, the rule, df beta in absolute value larger than 2 over square root n, that is this number, 0.075. And now what I simply do is I list the cases for which this is actually true. These are, let's say, potential outliers. Here I do this for the first variable, df beta 1. Show me the name of the player and the df beta 1 value if the absolute value of df beta 1 is larger than 0.075, that's that one. And because I don't want the df beta 1 equal to missing, I add and df beta shouldn't be missing. Now that gives me a list here of players starting from Batistuta all the way up to Joe Max Moore. And these are, let's say, potential outliers if you look at the df beta 1, which was the coefficient of height. Same thing, but now for the second variable, df beta 2. Let's see. Yeah, I should have typed the df beta 2 here, but this is the same list, but now based on that same command for df beta 2. And now I see here, for instance, that Batistuta, who was in the set of potential outliers here, is also in the set of potential outliers over there. Suggesting perhaps that there is something particular about him that makes him different from all the rest. And what I could do as well here, and I did that on the slide afterwards, is simply combine it. Okay, let's see which of these cases in the data are outliers in both senses. So I have my df beta 1, there I get a set of potential outliers. I have my df beta 2, again, a set of potential outliers. And I look at the players who are in both of these sets. And I end up with this group. 5, 10, 11 cases here in the data that are suggestive of, well, might be outliers of some kind. Okay, so I end up with a list of 11. Yeah.
To do this stata command, do we calculate by ourselves at 0.075 or stata does it for us?
Stata doesn't do that for you. You have to do this. Unfortunately. Yes?
Is it also needed for the second df beta that you take 0.075? So for that df beta it was 0.0078.
Yeah, the rule of thumb is not related to what the actual df beta looks like in the end. So that border of 0.075 is the same for all the df betas that you have. If you have 10 predictor variables, then it's the same for all 10. Okay, so let's see what we have here. There's another rule of thumb that I typically use myself, because as you can see here, let me backtrack to all these different rules. They're all different, which is kind of nasty to remember. You can check it, of course, what was the rule again? And I typically use something else myself, but generally works quite well. What you could do with these kind of things is, well, if I have my df beta variable, I can standardize it. I've standardized it, it now has a mean of 0 and a standard deviation of 1. So now I know what weird cases are. Anything way below -3 and way above +3, that's a weird case. So that you can try as well. I did that here. I created a standardized df beta value from df beta 1, same thing for df beta 2, and I'll do the same process. I'll get a slightly smaller list, and if you would compare the lists, you would see that in fact quite a few of these are indeed in the set that we had before. So now I end up here with a group of 6 of, let's say, potential outliers. And in fact, this is not more than that. You get a suggestion of these might be outliers and might be different from the rest. And it's up to you to try to figure out if they really are. That's the complicated part. So that opens up, first let me, the next question would be, okay, now these might be outliers. Now what? Now what do we do? But first, on how to calculate this stuff. Is that clear? Okay, now what? Well, the first thing to do is you end up with a bunch of cases in your data that are potential outliers. If that part of the data is really large, where really large is 15 or 20%, okay, this is simply throwing away too much of your data. Your model doesn't fit very well, apparently. Just try again and come up with a better model or with better data or what have you. But if all your cases are outliers, then you simply have something weird going on. Then the other thing would be I end up with a group of 6 or a group of 11. I look at these cases in my data and I try to figure out what they have in common. One thing that could typically happen is that I look at these, for instance, the players here, and I find out that that they are a specific group. I don't know, they're all smaller than 160, or they're not, but that could be an argument. And if I see that, and I figure out, wait a minute, all the ones who have weird values here, they're all very small, they're all below 160. Now what I would do is I create another variable here, another predictor. Is the player smaller than 160, yes or no? Yes, then a 1, no, then a 0, and I add it to my model. Sort of modeling away the fact that these cases are outliers. And then I try again, and check again, and in the end, I hope that I end up with no outliers anymore. If you eventually end up with, let's say, 1 or 2 outliers, you could argue, well, okay, this is 1 or 2, let's see what happens. I run my model once with all the cases, I run my model a second time, now with these cases out. If it makes a big difference, then I need to think about should they be in or out. If it makes a relatively small difference, then it doesn't matter so much apparently, and we need not bother too much about it. So the worst thing, to answer your question, what can happen is that you really found outliers in the sense that if I run my model with them in, and now I run the model and they are out, and now it makes a big difference, okay, now this is time to panic. Now you have to think really, really hard if they really belong to the data or not. For instance, in the experiment that Daniel did with the heart rates, you'll typically see people there who score, because for some reason the smartphone doesn't work very well, or who knows what, let's say 30 heartbeats per minute in the first measurement, and then the second one it does work, and then they score 88. Okay, obviously something went wrong there, and you could argue, okay, it's just measurement, so we have to include it and see if it still works with the 30 in there, or you could argue, yeah, that's obviously wrong, and I would normally also be able to see that this is wrong with the heartbeat of 30, you're dead. So you could leave it out, and typically we hope that it doesn't make so much of a difference for all the results. And the most important thing actually is, in the end, if you report about it, for all these things that you do might be reasonable, you might be able to find reasonable arguments, but you have to write them down. So what you don't want to have is that you see, if I take out these are all outliers, and now my model fits really, really good, and let's pretend that I didn't have these outliers to begin with. That's called fraud, and we're not supposed to do that. Okay, that on the outlier part. Any questions about this? The one thing I forgot to mention, by the way, is when to do it. And typically you want to do this, yeah.
What do you do if you don't have at least a little expertise? So for instance, with wine data,
Yeah.
how do you know if it's an outlier? What do you do if you don't know? If you cannot say that whether it's reasonable.
Yeah, let's say if you know nothing substantially about your topic, in a way, this is a dangerous area to end up in to begin with. But then I would be really wary to get rid of anything, and I would be tempted more to stick to the data as it was offered to me. I know nothing about wine. This is what I get. Okay, I'm going to go for it, and that's it. This you typically do, well, at least once at the end, when you think, okay, my model is complete, this is it, now check and recheck if I have any outliers. But you might also do it somewhere down the line, because what could happen is you're trying to find a model that fits reasonably well, and it doesn't work out so well, for instance, because when you check the assumptions, none of them seems to hold. And then creating a new model could mean, okay, trying to come up with different kinds of transformations, trying to come up with different kinds of interactions, or it could be trying to find a set of outliers that are messing up your model. And then you could find out, I find a weird bunch of data here, I somehow take them into account, now it works better, and then in the end, you want that if you double check that whether there still are any outliers, you hope that you find none of them anymore. Those are the good days. Okay, so this is what we went through. All about getting your data, and from getting your data, making sure that you end up with a model that is as good as possible, like a decent representation of what is in the data. So we think about which variables to include. Normally we do this before we actually collect the data. If you get it, a data set from somebody else, you think about which variables to include in the model. One possible recipe is transformations of your predictor variables. We looked at the frac_poly command and thought about, log of x or square root of x or 1 over x might work. If you have to make sure that your y variable is between bounds of different sorts, then you could transform your y as well. And the last thing that you can do here is actually look at interaction effects. You have two different variables, and you take the product of the two. That will also give you a new one. And we talked a little bit about what the arguments were to find variables like that. And in the end, outliers, that could also help if you find out the model still doesn't work so well, and none of my assumptions seems to work out, then that's also something that you could do. Okay, that was the last bit of the last lecture. Let's see. Okay, there we go. Third part. We had that long list in blue. The only thing that was missing was assumption checking. That's really the last thing that you have to be able to do here. As soon as we have that behind us, then in principle you're good to go. So this is really the mastery bit. It's also a long list of things to do, and that might, it's not always a nice thing to do, especially if you think that you have quite a decent model. Then you check all your assumptions and you find, they don't hold, and all the stuff that you did was, where you thought you were so smart, that in the end didn't work out. Okay, so the third bit is up to date, and we are waiting here. Assumption checking and all that we covered already. These are the data commands you'll come across. Regression now with an extra option called robust. Bootstrap, it's also something else that you can put in front of the actual regression. Different kinds of plots. VIF stands for variance inflation factors, and different kinds of tests that we need for our assumption check. So a relatively wide set of new commands here, all related to the assumption check. One other thing that I wanted to mention, just before I forget, is we're a bit behind. It's relatively usual with the wiki stuff. I had a couple of mentions of, okay, this wiki is done, have a look, and I sort of cleaned up and completed the whole thing. If we keep trailing behind, then what will happen is that the last days before the actual exam, it will be a zoo on the wikis, and everybody will type there, and nobody will dare to take anything out from somebody else, and it's not of any use anymore. So it's a good idea to try to use these wikis for your benefit as soon as possible, and not to wait for the last week, because then typically it's on the late side. It doesn't help so much anymore. Okay, then, regression assumptions. It's a bit like eating your vegetables. You know that it's good for you, but, you know, it doesn't taste so well. But still, in the end, you have to do it. So let's see, what do we want here? Regression assumptions, what should they guard? Well, two properties of estimators. One would be that the estimator that you're using, that multiple regression stuff, gives you the right coefficients. You want these estimated coefficients to be, on average, spot on, without any bias. That's the one thing you want. And the other thing is, well, besides the coefficients, you get the significances of the coefficients back. And you want these significances to be also to be right. And what's more, you not only want them to be correct, but you also want them to be, let's say, as tight as possible. So if you have a confidence interval around an estimate, you want that confidence interval as tight as possible to be able to say something as precise as possible about that coefficient. And if the assumptions that are supposed to hold for multiple regression do not hold, then either one of these or both could be out the window. So we have to know, first of all, what the assumptions are, then how we can trace if they are holding or not, and then if they're not holding, what to do about it. And in some cases there is something to do about it, in some cases there isn't. Okay, so for the more visually inclined, if this is my estimate of a coefficient, and this is my 95% confidence interval, then I want for my estimation procedure in general that the two values over there don't take something like this. This is way too much to that side. I'd like to have something that where I have a reasonable idea that my estimate of the coefficient is correct, and also that greenish confidence interval is as small as it can be. I'd like it to have it even smaller. It will get smaller if I have a larger n, but I sure as hell do not want that my statistical procedure causes me to have a really wide confidence interval over there. Okay, so, and just to convince you a little bit more that you actually need all this stuff, this is because we'll be using these models for real problems, right? So we're predicting the number of cheeseburgers showing up. If we do something where we run a multiple regression and we shouldn't have, then cheeseburgers are piling up and nobody's here to eat them, or the other way around, customers are piling up and there are no cheeseburgers to eat. Here too, you're hiring the wrong players, or you're creating the wrong website, or what have you. So all these things have real problems behind them, and if you don't do it right, then you come up with the wrong predictions. Okay, so this is the list. First, grayed out, because that is sort of obvious. An obvious assumption is y is interval, and we have numerical x variables, okay, otherwise we cannot run a multiple regression in the first place. And also the thing that I want to predict and the thing that I want to predict it from need to have some variance. If they are constant, then prediction is not so much, not much fun. Okay, so let's first name them, and I'll go through them one by one. One is called, there shouldn't be multi-collinearity. All the relevant predictor variables should be included. There should be homoscedasticity, there should be linearity, we should have independent errors, and these errors are supposed to be distributed normally. And that is sort of the semantic version of what you see here. So y is supposed to be a linear combination of these x variables. That should sort of work. There is a residual over there. It's distributed normally with a mean of 0 and a fixed variance sigma squared. And this is, for instance, implying, well, given that it's fixed, it should be equal everywhere. So the extent to which I miss my y, that shouldn't differ across the whole range of variables that I have. And in fact, all these we have over there are just another way to write, in fact, this. There it's a little bit easier to see. Okay, so one by one we go through these and we try to find the issues there. First, you shouldn't have what's called multi-collinearity. That is, your predictor variables should not be two alike. The reason for that is this. I mentioned this a couple times before. What you get is you get regression coefficients. What do they say? They tell you something about the net benefit of this variable, given that I have all the other ones in there already. If I look at the net benefit of this variable and I have 27 other ones in there that are closely related to this one, then the net benefit of this single one is close to 0, and you get nothing. So it may appear like all these 27 variables have no effect whatsoever. But the only reason why I find this is simply because you add them all together, because then the net benefit of each and every one of them is close to 0. Okay, let's see. So this is what it is. Multicollinearity is a strong correlation between two or more of the predictor variables that you use, and you don't want to have it. What do you get? Well, you typically see that these predictor variable, the coefficients, the estimated coefficients tend to go to 0 because the net benefit of any single variable is not that high. This is more an experience thing. What is called bouncing betas. Your estimates for your coefficients can change dramatically if you leave out one or the other variable. So what you typically do when you run a model, you try with a variable in there and another one, and then you look, okay, let's try this other one here. If now all the results are completely different, this is what's called bouncing betas. Your coefficients are dissimilar all the time, and that's also very often suggestive of the fact that you must have two or perhaps more variables in there that correlate quite a lot. Okay, how do we find it? Well, two ways to do it. One is simply to look at the correlation matrix of all the predictor variables. So if I have a big set of predictor variables, or a small one, let's say 10, I look at the correlation of all 10, and I check, do I find any high correlations in there? If you do, this is a recipe for trouble. I'll show you an example in a minute. And the second one is you calculate variance inflation factors. That's a new thing after running the regression. And these two things will tell you if you are in for this or not. And what can you do about it? Well, let's suppose that we have correlation between just two. Let's say a correlation of 0.99, so really high. This simply means, statistically speaking, this one and that one are the same. So there is really no need to include them both, and the simple cure is you get rid of one. Or you average them out and you add that one instead of the set of two. It didn't make any difference to begin with to include one or the other, so that's the standard solution. Matters are a bit more complicated if you have correlation between more than two, so it could be that 1 and 2 together correlate very highly with the third one. That's more difficult to find, but generally what you have in there is two variables that for some reason or another correlate too highly. Let's see how this goes. First, the easy bit, checking correlations. So here are the predictor variables that I use for the wine predictions, the vintage, the rain, the degrees, and more rain. And you see here that all these correlations are, well, let's say 0.27 in absolute value or less. That's usually nothing to worry about. So then the question is, okay, when should I start to worry? And the standard answer is, it depends. It depends because the more cases you have, the better you can get away with high correlations here. This is if you have a huge sample, thousands and thousands of cases, then even large correlation between predictor variables can be disentangled. But in general, there is reason to check, let's say, if there are correlations above 0.8. And above 0.8, I mean above 0.8 in absolute value, so minus 0.9 is also above 0.8. Then you have to check. Might be that there are two values in there. For instance, here you could have thought that, for instance, the rain in the winter and the harvest time is probably related. Well, apparently it isn't. Only 0.27, so nothing to worry about here. That's the first thing to do. And the second thing is to look at these variance inflation factors. Here I ran the actual regression trying to predict the price of the wine, and then I typed afterwards the command VIF for variance inflation factors. You get a list of variance inflation factors back, and let's see what that means. No, let me first give you the rule of thumb without knowing exactly what's going on. There are a couple of things to look at here. If you have one high value in there, in this fifth column, where high means, let's say, 10 or higher, double check if there is something in your data where you have two variables that are actually measuring the same thing. Or if, in general, they are all high-ish, let's say 2.5 or 3 or higher, that's also a reason to double check what happens if you would exclude one or two of your variables. And in fact, these numbers here are estimates where you compare how wide these confidence intervals would have been if there would have been no correlation between your predictors. Doesn't really matter so much. The easiest thing is to just remember where to look for. And the standard thing you typically encounter if you are in trouble is one high value. So that would mean, in fact, let's say if there's a 10 over there for degrees, that would say, well, degrees is related to some of the other variables here. And if it wouldn't have been, then the confidence interval that you have would have been 10 times smaller, which is kind of a large difference, and that is suggestive of the fact that there's something going on here. Okay, so that's the way to look at correlation between predictor variables, and immediately one exception, and the one exception are categorical variables. We have a categorical variable, we create dummies, 5 categories, 5 dummies, we include 4, and these dummies by definition correlate. Can't help it, because, you know, when one is 1, and the other ones are 0. So there must be correlation between the two, and the only exception to the rule of excluding variables that correlate too much is with these dummy variables. These you want to have included all. So all as a set, or none of them. But not let's leave just 1 or 2 of these 5 out simply because they correlate too much. Okay, so predictor variables not too much alike, because if they are, then you know all the results are messed up, and you get also less significant coefficients than you would have gotten if you would have gotten rid of the problem. Okay, that's only the first one. Any questions about this part? Yes.
Can you still run it with categorical variables and just ignore it?
Yeah.
Okay.
Yes, you can. Depends a little bit how much you are bothered by it, also on how the categorical variable is distributed. For instance, if you have a category in there that is relatively rare, so that a couple of 1s and a big bunch of 0s, that makes a difference for the kind of correlations you're going to get with the other ones. And generally, if these are nicely distributed, you're not so much in trouble here. So it is quite unlikely to get a 0.8 correlation in these kinds of data. But nevertheless, even if you do, in principle, you would like to keep them in. Okay, that was number 1. Number 2, all relevant predictor variables included. Good, you had that already. That was that stuff from last week. The only thing there to think about is, well, first, is this an experiment or a survey, and which of the predictor variables am I interested in the most? If it's an experiment, usually there's only one predictor variable where I'm interested in, namely the manipulation that I did, and then I need not worry so much about all the other variables. If it's survey data, and in fact, the two things that we need to have here is that first, the model should be equally good everywhere, which is called homoscedasticity. And if you don't have it, it's called heteroscedasticity. And you wouldn't believe what people write at the exam instead of this word. This is the right way to write it and to pronounce it, homoscedasticity. And the other thing is that the linear model should indeed be capturing the shape of y. We're assuming that y is the weighted sum of x's, and that should be
Sorry, what's the second one again? Because I don't have the motif here.
all relevant predictor variables included. Okay, it's easiest to see what's wrong if you don't have this graphically. And this is what the set of graphs looks like. Linearity is that the true model should be linear, or linear enough, so to speak. And homoscedasticity, all residuals are from a distribution with the same variance, that epsilon distributed as large N 0, sigma squared. That's where that came from. So this is actually what you want to see if the graph here put the predicted values in your model. So this, I'm predicting some target variable y, and I standardize it and put it here on the horizontal axis. And this is the residual, so this is how far off I am. And what I want to see in a graph like this is, let's say, pure noise, like the one on the top left. Then we're fine. What I don't want is something like this. Here you see that as my predicted value gets higher, the variance in my residuals also gets higher. So I'm quite good here. My predictions are relatively near the actual values. And it gets worse as my predicted value gets higher. Or stated differently, as my target variable gets larger, apparently here my predictions get a higher variance. You don't want it. Same thing over here. No, same thing. Something else that you don't want over here this typically has, well, more or less the same variance everywhere. If I look at that band of dots, it's more or less of the same width for the whole area of the graph, but it's not linear at all. There's something in it like that suggests non-linearity, also not good. And if you are really in trouble, you could have both. Here you see that certainly not linear, because that cloud of dots is going first up and then down. And I also see that here the variance is larger and then gets smaller towards the right. So these kinds of plots are predictive of trouble, except for the one on the top left. And by the way, in the example here, the heteroscedasticity shows because the variance is increasing here to the right and here to the left. But in principle, you could also have something like this, which is also not good. This is also not homoscedastic. Here you see that, okay, here the variance is large, then it becomes smaller, and then it becomes large again. Also wrong. So you want the variance to be more or less the same everywhere. Okay, so that's what it is. And one way to diagnose it would be simply to look at these plots. And that's indeed one way to do it. The trouble with looking at the plots is that these examples are also very suggestive, where obviously here you see the shape in there, and there you see that it is increasing towards the right. But if you see an actual cloud of dots from real data, very often, I might look at it and say it doesn't look homoscedastic to me, and you might think that it does. So we hope to find something else that is a little bit better than that. But let's see what we have here. So let's go through them separately. First, linearity. If that is not holding in my data, then the model can be totally wrong. I can have a real bias here. So from the two things that we want from an estimator, that my coefficients are in general okay, and that my confidence intervals are in general okay, I get that the coefficients might be wrong, which is from the two that we have actually the worst. And there are only a couple of ways to go about it, and the only thing is, well, do check these plots and hope that you see something in it. Consider if changing your model improves your results. That is in general the best way to go about it. Try to find as good as you can with predictor variables in your data seem to work. And one way to help you with that is use that OV test, omitted variable test command again. This one was also trying to figure out if your model fits, or it would be a wise idea to fumble around with your predictor variables a little bit more. So these are the things that you can do about it. It's not, not very concrete. It would be nice if you would have a command. For some other assumptions, we will see that we have an actual command. Okay, do I have linearity? And then you would like an answer. No, but that's not how it goes. You have to look at these different kinds of plots. For the other one, I'll show you in a minute how the plots actually work. For the homoscedasticity, there it's a bit, let's say, less bad. So from the two things that we want, predicting the coefficients right, and predicting the confidence intervals right. If we have heteroscedasticity, this is not good, but then still my coefficients are okay, but in all likelihood my confidence intervals are off. So that's less bad, still not great. For that you have actual commands, IM test, information matrix test, and head test. I'll show you those in a minute. So with these you can actually detect if homoscedasticity holds. And we have actual cures that are a bit more concrete than what I said before. For linearity, the only thing that I could say was, try to come up with a better model. Not good enough? Yeah, try harder. Here, you actually have something else that you can try besides standard regression that will save your butt. Nevertheless, still, trying to come up with a better model, that's always a good potential way out of trouble here. So try to come up with a model that fits better. But in the end, if you've tried everything that you can do, then the only thing you have left is these two things, using robust standard errors or bootstrapped standard errors. Okay, so these two together, usually you consider them also as a set. For that you need different kinds of commands, and here you see a number of post-estimation diagnostic plots. Multiple regression is weird in the sense that you typically need to do the checking afterwards. So you run a multiple regression, Then you do the checking, and the checking is about, okay, I ran the multiple regression already, but was I allowed to do that in the first place? So here you see, the first one, RVS plot, that is the residual versus fitted plot. That's actually exactly the one that we had there too. Residual was over here on the vertical axis, and fitted was on the horizontal axis. So the RVF plot actually gives you the plot that we saw in the examples. And this is what you see, or what you can see, for instance, so after you have typed RVF plot, so first you run your regression, regress y, x1, x2, and so on. Then you type RVF plot, you get a plot like this, yeah. And now you do that, you look at it, and you try to figure out, does that look like random noise? Not so easy. One thing is that it might help you also find some outliers. You could think here, this is sort of random noise. It's only that these 4 cases are there that is bothering me a little bit. So this is suggestive also that perhaps these are outliers in some sense and need some extra attention. But still, even here it's relatively clear. You could have something where you see basically nothing in there. Is that noise? I don't know. But it's the only thing that we have. Something else that we can use here instead of that residual versus fitted plot is what's called an added variable plot. If you have one target y and one x, then we're just trying to fit a line through a cloud of dots. If you have more predictor variables x, this gets to be more complicated, but we can try to work around that a little bit. Like this, if we have, for instance, 2, and we want to see in a graph like that what's going on, what we could try to do is first run our regression model, so now I get estimated b0s, an estimated b1, and an estimated b2. And if I'm, for instance, interested in a plot of x2 against y, what I can do is, well, I take this part, the b1 x1, or the b1 hat is now included. I bring that to the left of the equation. There gives me a new y, here, y tilde. That y tilde I use as my horizontal axis now, and now I have on the right side only one x. So from these, the y tilde and this one, I can make a scatter plot and have a look once again. And this is in fact what happens here. If you ask for added variable plots, it's hard to see I think, but here you see on which variables this was based. This was vintage, rain, and degrees. So this was again the wine data where we had 4 predictor variables. And if you want to see a scatter plot of y against each and every one of these predictor variables x, controlling for the fact that you have these other 3 in there, that's exactly what we see here. Very often it doesn't make any sense just to look at the scatter plot of y against x1, and then of the scatter plot of y against x2. Because in your regression results, they work together. And they are also sort of in each other's way. And that's exactly what you can try to abstract away from if you do it like this. Give me the added variable plots. What are the scatter plots of y against each and every one of your x's, given that I have the other 3 in there as well? And again, what you're looking for here is, let's say, any patterns that you don't want to see, anything that is either nonlinear, so wavy, for instance, would be typically nonlinear, any kind of cases that are totally weird, which is here not really happening so much, and any indication that you could have that the variance is not consistent across the whole graph. And as I said already, this is really hard to tell because you could argue, well, here, sort of looks like that the variance here is a bit larger than it is over there, but, you know, is that really a bad thing or is it bad enough? Hard to tell. But at least these plots give you some suggestions, for instance, on how to better model your predictor variable. If you would see here, let's say that the cloud of dots would not be like this because this is pretty straight, but let's say like that, going up and then to the right, then square root of degrees would certainly be a better fit. Okay, check for yourself which other post-estimation plots there are that might help you in trying to figure out why your model as it is not working good enough. But yeah, the point is, all this, it remains looking at plots, and that is a bit of a bad thing. For many statistical packages, that's the only thing you have. Try to open up SPSS, and then the only thing for diagnostics that you can do is looking at different kinds of plots. It's a good way. if it works, but you know, very often it's also not very instructive. So what we want to do is also use a couple of commands here, and for the homoscedasticity part, we actually have commands to test it. So let's see. I have here, let's say, a loose description of what the command that I'm about to show is doing. And first, let me tell you the easy variant. I have an H0. It's a statistical test, so it must follow the same setup that we have for all statistical tests, right? So we're looking for H0. What is the basic thing that we're testing here? Well, we're testing here the residuals have the same variance everywhere. We want to have that as true. Now, somebody smart with a guy called Hal White, came up with a test statistic, as we would like it. That test statistic increases and has a known distribution. If it's big enough, then we know that H0 is rejected. Now, I sort of assume away all the complicated stuff here. Here you see, by the way, the econometric paper from the 80s, where it was shown that this is actually true. If you want to know exactly how it works behind the scenes, and you can, in fact, indeed run it yourself. You can run the command itself in any case, but the different steps. This is what happens behind the scenes, and here you can also see that this is not so intuitive anymore, and why I try to extract away from it. You run your regression model, and you save the unstandardized residuals. That's easy. Run a regression, I do predict my residuals, fine. And now I have an extra variable in my data. I create another variable, it's called the residual squared. Also not very complicated. Now I compute squared values of all predictors and of all products of my predictors with each other. Okay, you know, don't see really why, but it's in principle not that complicated. Now I've got a bigger set of predictors. Now I run another regression where my y is that residual squared, and my x's are all these variables that I created in the previous step. Okay, now it starts to be weird. I mean, why would you ever want to do this? Now I compute n times the r squared that I find. N is the number of cases that I have. The r squared is the r squared from the regression in the previous step. And now, look at the paper if you're interested. We know that if the whole thing is homoscedastic, so that is what we want, this test statistic follows a chi-square distribution with the degrees of freedom equal to the original number of predictors. Okay, this is not intuitive anymore. So somebody else, luckily, thought of this, knows the procedure on how to figure out if the data is homoscedastic or not, and luckily Stata found somebody to implement that command as well. So as soon as we find a significant chi-square test there, a value below 0.05, we can say, okay, homoscedasticity rejected, and it's not what we want. Okay, Stata has this in different ways. In fact, besides the single way that I just described, there are two other ones that also test homoscedasticity, but in a slightly different way. So we have in the end three. This is the first one. IN test, white, it's an information matrix test, then het test, or heteroscedasticity, and het test, RHS, where RHS stands for right-hand side. Three ways to test for homoscedasticity, and what you want is that all of these are supported, that none of them is rejected, because they test for heteroscedasticity in different kinds of ways, and it should work in all kinds of ways. Yeah, they are the same in the sense that the H0 that is being tested is the same everywhere. Variance is equal everywhere, so that's exactly what you want. And you would like all these tests to be non-significant. And if one of them is not, then it's a good idea to do something else. Okay, in itself, not very complicated. The only thing that you need to do is remember the actual command and know how to interpret it. And here you see it happening. Once more, the wine data again. So I run my regression here with price as a target and all the other ones as predictors. And after that, here I do one, the information matrix test, white. And we get white's test for H0 is homoscedasticity. Great. And the other one is, well, unrestricted heteroscedasticity. And we see here, well, it's not rejected, but by a hair. It's just above 0.05. So in fact, here H0 is supported. And we're good to go. I think I have, yeah, I have the other ones here as well. So these are the other two. heteroscedasticity test. This is a bit misleading in terms of wording because H0 is again constant variance. So we are testing homoscedasticity here, even though it's called het test. And now we see value here 0.09. Again, above 0.05, great. H0 is supported, nothing to worry. And the other one over there is also further above 0.05. So also nothing to worry about. So for this one, there are no indications here that there is heteroscedasticity, or we're good to go with the assumption for homoscedasticity. Yeah.
Can it be that both tests predicted outcomes, so like one rejects and the other?
It is very possible that these three tests each contradict each other. Yeah, each is difficult because you have only a yes or a no, but you can find that all of them are supported, as you find here. You can find that one of them is supported and two are not. If at least one is not supporting H0, that's already reason to do something else. Okay, so here you can diagnose if you have it. Let's suppose that we wouldn't be so lucky as we are here, then what to do? Now we know we have heteroscedasticity, not good. Well, three solutions basically. The first one is the standard solution, and in principle the number one option. That is try again with a different model. Apparently a model doesn't fit the data very well, or not, at least not well enough to hold all the assumptions. So one standard idea would be to come up with a different one. But let's assume that you did all that and you're more or less running out of options. Then what can you do? Two other things. The first one is run regression with an option robust. This calculates standard errors in different ways, does nothing with the coefficients, and that in itself is also not necessary because that heteroscedasticity that didn't do anything wrong for our coefficients, it only affected the confidence intervals around them, and with this you're calculating these confidence intervals in a different way. So this is one way out of it. And the bootstrap command does actually the same thing, in the sense that where robust gives you a different way to come up with the confidence intervals, bootstrap also gives you a different way to come up with the confidence intervals. And they help. So let me first show you how that robust goes. You see it happening here. Robust standard errors. Yeah, there you have it. So you see first, command is exactly the same. Only thing that changes is the robust behind it. Does nothing for the coefficients. So these are all the same. But it does do something for the significance values. The stuff that's on the right over here. Here you see, well, let's check for instance first the column here on the right, 0.012 and 0.001. So in this case you could argue in principle that doesn't matter so much because it was statistically significant over here and it is statistically significant over there. A little bit more here than there, but still all on the same side of 0.05. And I think that this goes in fact for, yeah, well, depends a little bit. 0.05. No, I think that goes for all of them in this case, but in any case you see here that the numbers that you see over there are not the same as the numbers you see over here. Same for this column. These numbers now differ. The significance values are calculated in different ways, and you're good to go. Easy. In fact, there have been papers relatively recently that suggest that it would be better to type that robust always, even if you don't think that you have a problem of some kind here. Anyhow, that's not the standard, so we use this only when we have to. Then the second solution, that is also something where we have different kinds of confidence intervals. There, in principle, if you know how to run it, you get these different values here again, but I need to explain a little bit what it does, simply so that you know how it works. It's bootstrapping. And what is bootstrapping? Well, let's see. Let's suppose that we want to look at something else in a regression of which we do not have a confidence interval. That's, I think, the easiest way to explain it. Because for these coefficients, we have a confidence interval already. There's, no bootstrap, no nothing. I get the confidence interval. But let's suppose that I want to know something like this. R squared is 128. Could be, but, in all likelihood, that is not the R squared in the population. So I would like to be able to say something, well, it's 0.28 plus or minus a little bit in the population. And one way to do it would be through bootstrapping. And the bootstrapping procedure, irrespective of what exactly you want to calculate, is always the same. It goes as follows, it's kind of weird. Here, let's see, we have 74 data points in the data. So what I now do is, I draw a sample of size 74 from my data with replacement. Obviously with replacement, because if I wouldn't replace, then if I draw a sample of 74 out of 74, I can get my data. Right, so I don't do that, I take 74 out, and then after I took one, I put them back again. So what can happen is that case number 1 ends up in my sample of 74 here 4 times. Doesn't matter. I take that sample of 74, and I run my regression, as I did it here, and I check what the R squared now is. No likelihood, not exactly 0.2838, but something else. And I store it somewhere. Now perhaps 0.25. Okay, 0.25. Throw away that first sample. Again, I take a sample of 74 with replacement from my data. I get a new data set over here with a couple of cases not in there that are in my original data, a couple of cases more than once in there. I run my regression, and now again find an R squared, and the R squared is 0.30. Okay, I stored at 0.30. I repeat this process, let's say 10,000 times. Now I have 10,000 different R squares that I stored here. And what I could do is, I could make a histogram there of these R squared values that I now just stored. And the weird thing is, that this graph over here is, in itself, gives you a decent confidence interval for that R squared in the population. So what I will find is that if I do this 10,000 times, then over here, your likelihood will be about 0.2838. And a couple of them will be 0.4 perhaps, and perhaps a couple of 0.15. But if I take the 95% that are between these borders over there, that in itself is a good confidence interval for that R squared. So even though nobody gave me any kind of mathematical formula for what that confidence interval was supposed to be, I can calculate one simply by sampling from my own data. This is also why it's called bootstrapping. Bootstrap, like a shoelace, you're pulling yourself up by your own feet. Yeah.
Do you need a significant number of observations for this? Because I assume if you have only 10 or something, then it's weird.
Everything gets better the larger n is. So, yeah. I think that in general, let's say the conditions that you need for a standard regression are more restricted. So if you have, let's say, 10 cases, I wouldn't run a regression anyhow. And and then also I don't want to bootstrap. Okay, so, but as soon as I have a regression where there are enough cases to work with, then I would be willing to run a bootstrap as well. So the general procedure here is, okay, this is bootstrapping. First, from the sample that you have, you draw a sample with replacement, but with equal size to the data set that you have. It's kind of weird. You calculate the statistic that you're interested in. So in a regression, you look at the R squared, or in the case that we're aiming for here, you run your regression, and you do not look at the R squared, but you look at the coefficient of miles per gallon, for instance, and you store that. I had a confidence interval for miles per gallon, but that was dependent on that we have homoscedasticity here. And if we don't have this, then these are off. So basically, I'm now also in a condition where this, it's there in the output, but it's not right. I repeat that one too often, where often is at least a couple thousand times. I store it, and then I use the distribution that I get as a basis for the 95% confidence interval that I want. By the way, this is, okay, first of all, this obviously doesn't bring the same kind of amazement to you that it brought to me. This is relatively new stuff, I think end of the 20th century or so. And this opens up a lot of, let's say, simulation-based statistics, because here you need to know nothing. The only thing that you need to be able to do is draw a sample from your data. That's not that complicated. And run the analysis that you were running in the first place, and then you get all your confidence intervals for free. And the only thing that it costs you is a fast computer rate. So this is a cool thing in the sense that where we needed, we needed that Hal White from the 1980s to come up with a really complicated formula for all kinds of nasty stuff. And here we forget about white. You know, the only thing we need to be able to do is draw a sample and run a regression a couple times. Easy. Okay, so let's see how it goes. Here we have our regression again. Same thing. I've seen that a couple times already. What I ask now is, okay, Stata run me a bootstrap, and you have to mention how many replications that you want. Here I use 1,000. Typically, if I have time enough, then I'll use a little bit bigger number just to be sure. And then in the end, what you'll see, oh yeah, okay, you see here that in the results, first of all, these coefficients, once again, are not different. They're not changed by this whole procedure. But what you also see here is that the stuff on the right, again, has now slightly changed. The numbers that we see over there, we can see them over here. This is another way, besides the robust option, to try and make sure that that whole heteroscedasticity issue is out the window. And in a way, this is the easier one, because for this one we have an actual solution. Do something else, and then it might work. Okay, almost there. We now covered 4. We need to do a couple more, and then we're done. So let's see. Independent errors. Independent errors, what does that mean? Let's see. What I want to have is that if I run my multiple regression, and I would know what the residual value is for one case in my data, then that is not supposed to bring me any information about any other residual in my data. That's the idea. And how do we see it? Well, basically, we don't. The only way to figure out if this is happening, or almost the only way actually, is thinking about what the design is. And there are a couple of designs that you need to be able to recognize for which this is not working. For instance, for this one here, repeated measure. If I measure more than once on you know, we're measuring an IQ test 10 times for everybody here. So you have 100 persons in the room, times 10 IQ tests per person. Now that would mean if for one person in the room, I estimate, no, not for one person, if I run a model there, and I calculate the residuals, and I look at the residual for you, and that is the residual that you had for test number 2, and it's positive. In all likelihood, the residual for you on number 3, 4, and 5 is also positive. So I know something about the other residuals. This is not allowed. It's not independent data. And another way to think about it would be, if I would just run a regression, all the stuff that is being calculated there is then based on the idea that we have 100 times 10, or 1,000, independent observations, information from 1,000 cases. But really we don't. We simply have 100 times 10, and these 10 are sort of the same. We're measuring the IQ all the time, so in all likelihood all these numbers look like each other. Like a more extreme example would be, let's say that we weigh you 10 times. If we have a quite decent scale, we get more or less the same number all the time. If we run a regression as if all these are independent, the n that is being used there, is being used to calculate the confidence intervals, is simply wrong. So there's no bias, and coefficients are fine. But typically, if you disregard this, then what you get is that the n that is being used is actually too large, because 100 times 10, in this case, comes up to 1,000, but it's really not that. It's way less. And you have to take that into account. Okay, something else where you typically see this is with clustered observations. So if you have, let's say, pupils within schools, then you also know that, okay, if I have a bunch of pupils in the same class, and I know a little bit about how my model is predicting for that single person in class, in all likelihood it tells me something about the other person in that class as well. This is close to what the repeated measurements are, or time series data, for instance, the passenger data that we had in one of the wikis. If I know that this is data about today and tomorrow and the day after and the day after, then if I happen to know what the residual is for today, in all likelihood that tells me something about what the residual will be for tomorrow, for all cases close to it. Also something that you don't want. And there are two sort of cures. So most of the cures we will postpone for the next methods course. One is the robust standard error, which is kind of a cheap way out of it. You could try that. And the really good thing to do would be what's called multi-level modeling, but we'll cover that later. And in fact, bootstrapping is complicated here. So forget about this. The main thing to recognize is, look at the design, what has been collected here. Would it be likely that we have groups of data, clustered data, that stick together instead of independent observations? explanations. If we do, bad news. Yeah, and this I wanted to mention just to make sure. These passenger data typically have this issue. Okay, then the normality assumption that we needed as well. We assumed that that residual thing that should have a shape like this. Well, normality testing, we knew how to do that, so we know our way out of this. Relatively easy. What do you do? Well, you could do a couple things. Look at the plots of the residuals. First of all, you need to calculate the residuals. I have a model, I calculate it. I calculate predicted y. I look at the true y minus the predicted ones. That's the residual. And then I find the graph that goes with it. And then you hope that it looks like a normal distribution. And there are, of course, easier ways to do this because we know the SWILC and the SK test command, which is testing for normality, in fact. So we simply test the residual and check if it follows close enough a normal distribution. And luckily, it's even less bad than that because the rule of thumb is, well, as long as you have a large sample and over 600, don't bother. Even if it's not normal, forget about it. It's not so bad. If it would be a real problem, then what would happen is that your confidence intervals are not right. So the bias is not an issue. The standard cure is obviously, again, try to fit a better model, or, once again, use these robust standard errors or these bootstrap standard errors. That was a solution for heteroscedasticity. It's also a solution for non-normality. Okay, so how would that go? In a way, nothing new. We regress here, same thing. New command, perhaps, I'm not sure if we saw it before. Predict. E is the name of the variable that will show up in my data. And I add resid for residuals. So now I'll get a new variable in my data that's called E. All the residuals are in there, and I test now E for normality. And here you see, okay, normality here is supported, and here normality here is in fact rejected. So this doesn't hold the normality assumption. Okay, then some weird thing that I just want to add in so that you know. The nasty thing is that all these normality tests work best, than most tests do, when n is really large. Okay, but when n is really large, we don't need it, because for n over 600 we do not mind so much anyhow. So we really need this when n is small, and that is exactly also where the tests are not very good. So in a way this is a bit strange. But still, so here we see normality is violated, and one thing to do, oh yeah, there we see it. Okay. Not sure why that happened, but in any case, we see here that one of them is violated. And one thing to do would be add the robust option, and it would be good to go. One more, it's in a way not really an assumption, but nevertheless important. You shouldn't have too many non-significant predictor variables. As long as you have data sets, as we have seen up to now, at most, let's say, 10 predictor variables, then you can simply forget about this. If you have one in there that is not statistically significant, you could just leave it in, and it doesn't bother so much with all the other findings that you'll have. If you have a larger set, let's say 50 variables in your data, and for some reason you want to try them all at once, I suggest first that you think about this real carefully if you really believe that each and every one of these 50 would actually add to the prediction that, let's say, that you do, and then you find that 40 of these 50 are non-significant, so do not add anything to the prediction. At that point, and you try a little bit, a couple of transformations, and no, this whole set never does anything. Okay, get rid of it. It will. Otherwise, if you have too many of them, yeah, basically what you have is you're sort of looking at the true results through a haze of non-significant noise, and that might mess up the results at least a little bit. So if you find out that you have a big bunch of variables that are non-significant, get rid of them. If they are just a handful, I would simply leave them in. And for many cases where you do not have so many variables to predict with, it might be useful to actually show that the variable that you do have is not significant, because somebody else might think that it is. So, I think there is a difference in terms of, males and females differ on this or that. And I have that variable, and I find that it doesn't make a difference, then at least I want to be able to show it. So there might be reasons to include a non-significant predictor, even if you thought that it shouldn't have an effect to begin with. Okay, so all the arguments that you need here to include some and others is first the other ones. Usually before you, people have thought about which predictor variables to use and why. Okay, these you want to include. Others have done this before. Then you might have new ideas of yourself, or have heard of new ideas yourself that you want to actually test. Okay, we know this one should be in there because others did it before, but I think that these ones matter as well. So let's add those. Then you get rid of all the stuff that never turns out as significant. So in the end, you've tried quite a few of these models, and then you might find, oh, male, female never does anything. So, and in the end, you would like to skip that. And then still, whatever is, let's say, close to statistically significant, leave it in. Too often I see also at the exam, okay, I have a first analysis of my data. I've tried 5 variables. Okay, not significant, not significant, not significant. I throw them out and you never see them again. Okay, this is typically not what you want to do. What could happen is you add a couple of variables and then the ones that you just threw out would have been statistically significant if only you would have still had them. But then they are left already. Okay, last slide here. One example that I want to mention in particular. All this has to do with the fact that you want to be able to say something in the end that makes sense. Okay, I think that I can predict this target variable y, and I think that I can do it in a good way. One example from my own research, we have, it's now offline by the way, but an app that's called Spot that predicts skin cancer diagnosis, or actually precursors to skin cancer. And this is available in fact also for free as soon as it is online again. And here you're saying to people, okay, I think that you have nothing, or I really think that you have something here for which you should go to an actual physician. So you better be damn sure that the model is actually really working and that all the statistical significances are fine. Because otherwise what could happen is, because you are doing whatever sloppy thing that you are doing, and are sending people home who actually have something, or are sending people to a physician who need not have been there. Okay, a couple more things left that I want to emphasize, because they are slightly different also from what's in the book. Here, stepwise regression. Depending on which other course you're in, you might hear different stories as well. Stepwise regression is a procedure where if you have a big bunch of predictor variables, let's say 50 or so, you tell Stata, look, here are my predictor variables, there are 50 of it, good luck. Just give it a try and try to figure out which subset of those 50 is best. And I think it's a bad idea. There are a couple reasons for this. And, well, the most obvious one is, you can imagine that if you have 50 and you tell Stata, okay, go try, what we have is an alpha of 5%, which means that in 1 out of every 20 cases, we will conclude that there is an effect, even though there isn't, just by chance. That's how statistics is done. And if I have 50 of these variables, and I tell Stata, okay, throw them around and start thinking about which ones you should include. There will be lots and lots of testing going on there. In 5% of these tests, we're going to find something that appears to be statistically significant, which is just by chance. And in fact, the way in which Stata or any kind of other program does it is, well, it starts from, for instance, an empty model, like my target variable over there, and so I have my big bunch of 50. And I do this following. I take the first one. Okay, is this working to predict very well? Okay, let's no, set it aside. Second one, so that's better. I do that for all 50. I take the one that works best, let's say with the highest R squared. It's not exactly that. Let's assume that it is. Okay, now I leave this one in. Now I have 49 left. I do the whole thing again. I take number 1. I add this one. Does it help a lot? Okay, let's put it aside. Second one. Does it help a lot? And then again for all 49 until at some point I reach, okay, now I've tried the 23 that I have left and none of them adds anything. So let's stop here. So now I'm left with, say, 27 over here that are in the model. And that is the best model according to the state. Okay, so one problem is I did first 50 tests, then 49, then 48, then 47, then 46. In 5% of these cases, I'm going to find something just by chance, so I'm bound to end up with something there that is really not there. So that's one issue. Second issue is, that was only one way to do it, because there was another way to do it as well. This was forward stepwise. Backward could be done as well. You have 1 y and 50 variables. I put them in all, and I start taking them out. Okay, which one is the best to take out? Really the worst. Okay, that one I put to the 29 that I have now left. I take the one that's the worst, I put it to the side. Now what you would hope is that both procedures lead in the end to the same 27 being in. And that need not be the case. And this is when you have only 2 of these procedures, and there are more. And not all of them lead to the same subset. So this, it's easy because you don't have to do the work, you do go for it, and let's see what happens. But it's a dangerous way to go about it, because it's very, very likely that you end up with results that are really not there, even though this data, if you want to, you can get it as for stepwise, and then you'll actually get the stepwise results. Okay, so this is the part where the standard multiple regression run is your typical exam stuff. You get data, and the assignment is do something that makes sense. We're trying to predict this, and here's your data. And then you go about it. You check your coding errors, you check your predictor variables, you check all the assumptions, you run your base model. Here there is an iterative part. You try to make it better until it, let's say, is as good as it can be. And then in the end, you try to come up with what is the most appropriate model. One thing that is important to realize is that typically for the data that you get at the exam, as in real life, I do not pre-check these data. So it's not that here you should, let's say, keep plowing around until everything falls in place. Okay, because you're going to get real data, and all likely it won't fall in place. If it's really bad, and it has happened, in fact, then here you'll find it's not working. I can come up with nothing that makes sense here. And then the right answer is, I tried this, I tried that, the whole toolbox, and there is nothing there that works. And that turned out to be the right answer. So be warned that, don't get into a panic mode here if it's not working. That's just how it